I'd like to take you through a bit of the TomTom story and talk to you in the next 25 minutes or so about how we make maps and how we use artificial intelligence in that. First, I'll give you a very short overview of TomTom as a company, just to put it in context. Then I'll talk about how we see maps, what a map means to us, and how we think it can be used in autonomous driving applications. And then I'll get to the core of how we make these maps right now and how we want to make these maps in the future, building on technologies such as AI and crowdsourcing. So first, very briefly about TomTom. We have a heritage in maps, software and real-time services, going back to 1990 when the companies that eventually became TomTom first started out making digital maps of the world. Since then we've evolved. You may know TomTom best from our consumer devices on the right here, but our focus now is increasingly on the left, on the business-to-business elements, and I'm from the first column here, the automotive business segment, where we deliver to OEMs and to tier 1 suppliers, integrating our components, maps, software and services like traffic into the dashboard, into the systems in cars. That means in automotive our focus has also shifted. We started with embedded navigation devices, pretty much like the consumer electronics devices, but then slotted into the dashboard. Now with cars becoming connected, these applications need to become connected and smart, and increasingly enabling automated driving. And then perhaps slightly further into the future, we also keep our eye on what this will mean for mobility services once you have increasingly automated cars. Good, that's about TomTom. Now let's talk about our key product, maps. Right? What is a map? To us, a map can consist of many different layers. Layers for different representations of the world, for different applications. Right, there's a navigation map, there's ADAS content about the gradient or the curvature in the roads. There's a high definition layer that gives you high definition road information. Localization content, layers that could help as a reference for the sensors. Real-time updates of these layers, and on top of that, live layers, traffic information as we know it for navigation systems, but for automated driving systems you would need additional information about hazards, about slippery road conditions and so on. So from this set of layers, in a sense that we make in our backend, representing the world, we make different subset layers for different applications. For a navigation system, we create what we call an SD map, standard definition map, that has all the routing layers, all the naming, all the points of interest that you can search and plan a route to. But then when it comes to automated driving, there's a very different need, so it's a different subset of layers. Right? Here it really becomes about the precise information about each lane on that road, and knowing which group of lanes is going straight, which group of lanes is turning, what the markings are by the side of each lane, what the precise three-dimensional geometry is, to an accuracy that is much, much better than what was needed for navigation systems. And this is the map that we're now rolling out. We're rolling out the HD map layers on top of the SD map layers for the highways to start with. We've mapped all the highways in Europe and the US to that level of accuracy that we think is needed for automated driving. And that's typically on the order of 10 centimeter accuracy in relative terms, on a globally consistent scale. So really driving coast to coast in the US, you would still have that accuracy with that HD map layer. Then what does this HD map do in an automated driving system? Well, we think it can play a number of roles, right? Starting from the navigation, you would still, even in an automated car, as a user, need to find your destination and enter this somehow, be it on your smartphone or in the car. And then getting into that car, that autonomous driving system needs to localize itself in that map. It can use the map in perceiving its environment and building a model of what it sees around it, and then in the detailed path planning. Much more precise, a much shorter range perhaps than what you would do in navigation, really knowing what's up ahead beyond the range of the sensors. So I'd like to touch on each of these three uses in automated driving in turn, starting with localization. There's different approaches to localization, and as a map maker, we think we should be agnostic to the particular approach chosen. There's object-based localization, which could be features in the map, annotated, labeled, that could be matched against sensor observations to achieve a more accurate positioning than with GPS alone. These features could be things like the lane markings that help your lateral positioning, traffic signs that help your longitudinal positioning, and so on. But then we've devised another set of layers that we see as continuous sensor reference layers. And these are not labeled, not annotated, but really provide a reference on the sensor signal level. And therefore, they require less processing and give a continuous reference. So we call this family of products road DNA. And the one that I show here is the road DNA depth. It gives the lateral depth to the nearest object by the side of the road in a very compressed form. And if you were to compare this, as in the bottom picture there, against the observations done by a car, right? It might have a LiDAR to measure these distances, and then you can compare that pattern, the gray and white image there in the middle, that you have in the map as a layer, compare that to what the sensor has seen to really enhance the localization accuracy in that map to 10 to 20 centimeter accuracy. Now, localizing in itself is perhaps not a goal in itself, right? But localizing in the map will then help you to use the other map layers. First of all, for helping to perceive the environment. And just taking an example here of a typical radar observation, the raw sensor data is quite messy, but then if you superimpose those observations on an HD map, that would really help to make sense of these observations. It would really help to work out which are the cars that are in your lane that are important to you, which are the cars on the opposite lane that are unimportant to planning your own path. And that takes me to the final thing, the path planning. Right? If you have localized yourself in a map, then you can use all the other map layers, including the live layer about the hazards and the road conditions, to plan a path on a detailed level. And that helps to fill in occluded information. Your sensors might not be able to see around the corner or behind that truck. The sensors might also not be able to see that far ahead to make the ride comfortable. And combining the map information with the sensor information can make that sensor range longer and can make that automated drive more comfortable. So in these types of applications of our map, we're working already with a number of parties. Just to name a few here, there's OEMs like Volvo, and there's tier 1 suppliers like Bosch, Nvidia, Qualcomm, in China, Baidu, and there's others that we have not gone public with. So that's enough for the sales pitch. Let's then dive in further into how we make these maps. In making maps, traditionally we've used sources that we control. Right? We have our own fleet of mobile mapping vehicles. We do field surveys. We source from authorities, governments, and road operators. And we source data and fuse these into a map. But increasingly, of course, crowdsourced data has become important. And we've designed a platform in the back end over the last 5 to 10 years that we call our intelligent transactional map-making platform that combines these different sources. And let's zoom in on each of these a little, starting with the mobile mapping van. The mobile mapping vans that we have are equipped with an enormous range of very expensive high-end sensors. Right? There's not only 360 cameras, but there's also 2 LiDAR scanners on this, and very accurate positioning with GPS and IMU, the inertial mass unit. And that gives us very detailed data, such as the 3D point cloud that we can process in the back end. And the amounts of data coming out of these sensors, you have to imagine, it really is a stack of hard drives every day. It's not the typical data that you would upload to the cloud over a mobile connection. But it's a very rich set of data that enables to then apply increasingly automated processing techniques. And this is the first area where artificial intelligence comes in. Right? Because when we combine these different sensors, just to give one example, in recognizing the traffic signs, we can start with the flat surfaces that the LiDARs have detected. And then we can, for those flat surfaces, use the camera images to take these snippets of those flat surfaces and feed them into our trained networks. Anyway, we also then have operators who have labeled these, and we've by now created an enormous set of traffic signs with all the different implementations that traffic signs have in different parts of the world. And with that set of labeled data, the algorithms now detect the vast majority of traffic signs automatically. Where not, of course, the fallout, we still have operators who then annotate the fallout so that the algorithms get better and better. And as you see here, right, a sign that has a number 100 on it can still mean different things, and the algorithms need to be able to pick that up. And then, of course, that product, right, gets put into the map. All the traffic signs end up in the map. And all of this, as I said, is kind of based on our offline processing of the data that we collect. Let's now move over to the crowdsourced data. Crowdsourced data, the most basic form of crowdsourced data is just GPS probe data. And this is something we've used already for more than a decade. We collect now GPS probe data, literally just location traces, pearls of location traces from over 500 million users of our products. And that's across the different implementations on smartphones, embedded systems in cars, it's fleet management solutions, and it is also our old consumer electronics devices. In total, these probes give us such a detailed view of what is happening on the road in real time that it allows us to create very precise traffic. So here I just have an example of the A10 here around Berlin over kind of a 1 hour time interval, and every line here is a probe, a car, right, that has either a smartphone app or an embedded system and so on that feeds us its location. And the color represents the speed, so it's obvious over this horizontal distance between this junction and that junction, there is a delay, there is a traffic jam. And this bar here and that one there is then the resulting traffic message that we send back to the community of users. And these GPS probes are not very accurate, right? GPS can have an error of 10 meters or more, but still we are to a reasonable extent able to map each probe onto a different lane because we know its trajectory. It's not highly reliable, but good enough to identify if there's traffic jam on an exit ramp compared to the lanes going through. So that's also what we call turn-dependent traffic that we can detect from these traces. So this is real-time use of GPS probe data. Now we also do offline use of those traces to detect map changes. So where the road network has changed, and in this case is a junction here in junction in Portugal, you can see that over these months gradually a new roundabout was constructed. And I call this on purpose map change detection. This is just in a sense, the first level of using crowdsourced data. It's not yet accurate enough to make the map change, but it flags that something has changed, and then we need to use the other sources to make the change in the map to reflect the changed reality. And this is now where we think the next step is coming in. With cars now increasingly becoming equipped with sensors, more accurate, richer sensors, and cars becoming connected, this is the opportunity to get more data in than just GPS traces. And the first use that we see is actually for cameras. So there's a whole range of sensors, of course, available, but cameras are very cost effective, In our mobile mapping vehicles, we use LiDAR because we're not constrained. It's a relatively small number of cars. But for the millions of cars on the road, the low cost of the cameras means that they're being adopted very quickly already. So what we need to do now is devise a way to very effectively source the data from the crowd, from these cameras, and send them back into our map-making backend for map maintenance. And what we therefore need to do is do much more image processing, work out what we call a roadogram could be, kind of a very compressed form of a changed road that can then be fused and fed back to the community. So we built up, over the last few years, we've built up increasing teams on this in Amsterdam, in Poland. We also acquired a company right here in Berlin, a company Autonomous, that has really boosted our abilities to do these types of camera processing. And I'd like to, there's a lot of ongoing work in this area, but I'd like to share a few recent developments in this space. Our first one is semantic segmentation of camera images. So the colors superimposed here on this short video represent the different types of things that a camera sees. And this is a neural network that we've trained and that we had trained on a certain set of roads and then applied to other roads to see if it works. And you see it works out there, the parked cars, the trees, the buildings, and so on. Here, important, it identifies also the signs, it gives them a white color. So there's a high probability, and this is, in this case, just a frame by frame. We're not yet using the temporal link between the different frames, but in every frame, the probability of an object being a tree, a building, a road, or a sign, and so on. Now the signs, the traffic signs is an important thing that we're building further on. So what we're doing is also going there into the instance-based detection. Right? So a traffic sign might appear in all these subsequent frames. In the subsequent frames, you might have two traffic signs close together. They're identified as there's a high probability of having a sign there, but we want to cut them out separately. So this is then a separate algorithm that detects the instances of traffic signs, and these can then, the most probable, the non-maximum signs are filtered out, and the most probable sign is then fed into the traffic sign recognition algorithm that I talked about before. But keep in mind, right, we're doing this to feed into the map-making backend, so it requires a certain amount of onboard processing to create these short snippets that are then valuable in updating the map. A second example that I'd like to share with you is on the lane geometry. As I said, in automated driving, we think the map needs to be accurate, highly accurate to the lane level. So we need to know precisely where each lane is and what the markings are. So the same approach there we've used for this, what we can really consider a crucial component. In our map making, map creation and maintaining, the lane information is essential. And then in the use of that map, you would do this similar thing in the car to navigate, to localize, and keep the car in that lane. So, what we think, and I think this is also covered this morning in the presentations, is that we think we need deep learning, right? The kind of straightforward image processing techniques from maybe 10 years ago cannot handle differences in lighting conditions, occlusion by traffic, different weather conditions, and so on. So we need to apply deep learning techniques here. And the approach that we've taken here, or that we're currently taking here, is as a first step, use the CNN approach to obtain a pixel level probability of finding a lane marking there. And this is still on the per image level. And then as a second step, post-processing, to stitch these together and actually obtain a geometric representation, a piecewise linear line that gives you the road marking there, even when it's in some of the frames obstructed or difficult to see. And we've tested this in a public benchmark, this Q Simple benchmark, just before summer, July. And this is a kind of a public benchmark with a rather large training set and then a separate test set with no labels. And our approach, which admittedly only used a limited training set that was provided. Some of the others, I think the best team actually also used ImageNet and a lot of other imagery. But just based on this training set, using our neural networks, we achieved a very good accuracy, close to what the winners achieved. And of course, crucial here is how well we did on these difficult things, like in traffic conditions, in poor lighting, and so on. And fortunately, this turned out to work rather well. So here's an example from the training set where we do have the reference data labeled what it should be, and these were our results, our automatic prediction coming out of that. Similar example on the test set where there was no labeled reference, and we had these probabilities, and we achieved then these lines also where the lines are very hard to see because they're erased or they've been driven off the road or they're occluded by other vehicles. So let me conclude then by how we envisage that we will use this in what we call the closed loop of our HD map service. Right, I've talked about how we use traditional services to create our standard maps, our high definition maps, and our real-time map layers. These of course need to be delivered and used in the vehicle, increasingly for applications in automated driving, where they are matched against vehicle sensor data. There's a bit of information here on how we think that could be provided to the vehicle, because for automated driving applications you don't need, in our view, a coast-to-coast map of every continent. You really just need to have the HD map along the route that you're planning to take. Maybe a little bit by the side, but it could be relatively limited data, and therefore it could be streamed to ensure that you have the latest and greatest information on the relevant map layers. But as I said, it's about closing the loop, right? It's the final step here that, in our view, this artificial intelligence in the vehicle in creating sensor-derived observations, or these rhodograms that I talked about, these little pieces of information from the crowd of users of that map will close that loop and will make sure that the map is up to date at a very high speed. So the latency of any change being processed through this loop is something that we want to really get down. With increasing amount of usage, the speed of providing updates will go up. So that concludes my presentation. There's still a lot of work to be done in this space, we think. It's very exciting, and we think that we will help with this loop to make automated driving a reality sooner. Thank you.